we start linear regression today. So we finished the first two chapters of the book. Previous two sessions were getting experience in the basics of R, and we're hopefully going to be applying this in the labs at the end of this chapter. Just a quick refresher. We designed two types of models, at least where this book is concerned: regression models and classification models. This specific chapter is looking at a specific type of regression model where we are assuming linearity between the predictor variables, your x1, x2s until xp. That's just the notation that we use. P representing the number of input variables. And that linearity is between those x's and the output y. It is a numerical y. Think of time, income, height, weight, anything which can be measured on a continuous scale. Let's have a look. This chapter is about linear regression, a very simple approach for supervised learning. In particular, linear regression is a useful tool for predicting a quantitative response. Linear regression has been around for a long time and is the topic of innumerable textbooks. Though it may seem somewhat dull compared to some of the more modern statistical learning approaches described in later chapters of this book, linear regression is still a useful and widely used statistical learning method. Moreover, it serves as a good jumping-off point for newer approaches. As we will see in later chapters, many fancy statistical learning approaches can be seen as a generalization or extensions of linear regression. So it's just a great place to take as our starting point. Linearity is, go back to your secondary school education, the first curve that you study in the XY plane on your graph paper is inevitably a linear curve, and then you extend to parabolas, ellipses, higher order polynomials, and I expect a similar approach from this book. But this single chapter, it's where we really get into the details, and there is no other way of modeling, getting into modeling, that is, than starting from linear regression. Consequently, the importance of having a good understanding of linear regression before studying more complex learning methods cannot be overstated. In this chapter, we review some of the key ideas underlying the linear regression model, as well as the least squares approach that is most commonly used to fit this model. So you have your model types. We're looking at regression. This is specifically in this chapter, linear regression. How are we going to create a linear regression model? How are we going to estimate the parameters? Well, we've just read one way of going about it is this least squares approach. And speaking of these squares, it's been a while since we last mentioned the mean square error, the MSE, and that's square as well. In fact, we're going to pass that line or that plane or that linear, doesn't necessarily need to be a curve or a surface, depending on how many variables we're using. But if it's one input variable, it's a line. And if it's two input variables, it's a plane. we're going to get the best line, the best plane, and so on by using this least squares approach, minimizing the training mean square error. Recall the advertising data from chapter 2. Figure 2.1 displays sales in thousands of units for a particular product as a function of advertising budgets in thousands of dollars for TV, radio, and newspaper media. We are referring to these three charts over here. The blue, well, that's our model, and that is a linear regression model. We are trying to fit a linear relationship between the units of sales against TV budget, radio advertising budget, and online, actually it's newspaper advertising budget. Back to chapter 3. Suppose that in our model, let's read it again. Suppose that in our role as statistical consultants, we are asked to suggest, on the basis of this data, a marketing plan for next year that will result in high product sales. What information would be useful in order to provide such a recommendation? Don't forget that you're always working against a budget. There's no company out there that has unlimited resources. It may feel like that sometimes for some of the larger ones, perhaps, but it's just there is a finite. There's a whole study of economics, right? You're looking at scarcity. So our campaign for our specific product, and this will vary from are you, is it physical products? Are you what's your geographical location? What's your target audience? Their age groups? What are the demographics that you are selling to? And all these considerations are going to result in perhaps an optimal or a recommended. We're discussing statistical consultants. The whole point is to put forward recommendations as to how to perhaps balance a specific advertising budget. Let's say that the head of marketing has been allocated $500,000 for the next 2 years. How are we going to apportion that budget across TV, radio, and newspaper? Naturally, an effective marketing campaign, or to measure the effectiveness, one of the key considerations is, have the sales increased and to what extent? Here are a few important questions that we might seek to address. Is there a relationship between advertising budget and sales? That's as a basic, right? Can we influence the sales volumes by putting more resources into advertising? Our first goal should be to determine whether the data provide evidence of an association between advertising expenditure and sales. And the book is saying it right now. If the evidence is weak, then one might argue that no money should be spent on advertising. You want to see that there's at least some correlation. Now, the usual quote is correlation does not necessarily imply causation, but if there isn't even any correlation to begin with, then we might be focusing on the wrong problem on the wrong assumption that we can even influence sales volumes using advertising. So that's the first thing. Can we statistically speaking, can we quantify the relationship in order to conclude how strong that relationship, if any, there is between advertising and sales volumes? And this is the second point, how strong is the relationship between advertising budget and sales? Assuming that there is a relationship between advertising and sales, we would like to know the strength of this relationship. In other words, given a certain advertising budget, can we predict sales with a high level of accuracy? This would be a strong relationship. Or is a prediction of sales based on advertising expenditure only slightly better than a random guess? Then this would be a weak relationship. One famous study, this is going back a while, maybe 1950s. I think there were sort of two teams, and they had to pick stocks. So they were given a budget, but it wasn't an advertising budget. It was think of an investment fund. And they had to maximize the returns picking stocks. And in this specific study, now there's always the case of, if the study was carried out again, how replicable are the results or the conclusions. But one team literally picked the stocks. They had like I think a list of the S&P 500 companies hanging on the wall, and they picked the stocks by blindfolding members of the team and throwing darts at the charts. So that would be in fact it was proven that there were little differences between those that were doing like fundamental analysis and looking at companies' past performances and the team that was picking the companies, picking the stocks 100% at random. Which media contribute to sales? Do all three media, TV, radio, newspaper, contribute to sales, or do just one or two of the media contribute? To answer this question, we must find a way to separate out the individual effects of each medium when we have spent money on all three media. And over here, demographics come into play. If you want to reach a certain age group, you're not necessarily going to use the same allocation between TV, radio, and newspaper than you would with perhaps an older age group. How accurately can we estimate the effect of each medium on sales? For every dollar spent on advertising in a particular medium, by what amount will sales increase? And how accurately can we predict this amount of increase? How accurately can we predict future sales? For any given level of television, radio, or newspaper advertising, what is our prediction for sales? And what is the accuracy of this prediction? Kind of you comparing your Y hat against the actual Y. So actual versus expected, AVE. Is the relationship linear? That's what we're hoping for in this chapter. If there is approximately a straight line relationship between advertising expenditure in the various media and sales, then linear regression is an appropriate tool. If not, then it may still be possible to transform the predictor or the response. This is a very common theme. You take your data and you transform it. Maybe you take your raw numbers and you put them on a log scale. You transform them. In fact, not at mathematics A level, but this is a question that comes up at intermediate, not in a statistical context, but there's a, students are given an exponential relationship, but they transform the data so that the chart, instead of plotting y against x, you plot, for example, log y against log x. And in that case, the data points will roughly land on a straight line. And final point, is there synergy? This is known as interaction among the advertising media. So perhaps spending 50,000 on television advertising and 50,000 on radio advertising results in more sales than allocating 100,000 to either television or radio individually. So it's not simply, okay, I'm spending 100,000, can't I just put it all in television? In marketing, this is known as synergy. In statistics, it is called an interaction effect. And the result that it would have on the model, if I could perhaps just give you a preview of this, is that besides having a TV budget variable and a radio advertising budget variable, you'd have another variable that kind of allows for television and radio. And that would known as a that we would refer to that as an interaction variable or as an interaction term. It turns out that linear regression can be used to answer each of these questions. We will first discuss all of these questions in a general context. Isn't it a great book? Always starting with the big picture, even within individual chapters, at least as far as this specific one is concerned, and then return to them in the specific context in section 3.4. So let's begin. And we're going to go over many of the key ideas that we started out with at the start of these sessions in chapter 2. Simple linear regression lives up to its name. So apparently, not only are we doing regression, it is linear regression, and it is simple linear regression. I wonder what they mean by simple. Maybe it's just one input variable. Let's have a look. Simple linear regression lives up to its name. It is a very straightforward approach for predicting a quantitative response y on the basis, there we go, of a single predictor variable x. It assumes that there is approximately a linear relationship between x and y. So we say approximately, there is approximately a linear relationship. So it's just x to the power of 1 and no other terms or functions. There isn't square root. There isn't square root or sine or cosine between x and y. Mathematically, we can write this linear relationship as y is approximately modeled as beta naught plus beta 1 x. We will sometimes describe 3.1 by saying that we are regressing y onto x. For example, x may represent TV advertising and y may represent sales. And is there this data in R? Were we to load the library ISLR and ask R for the documentation of ISLR, and that never seems to work, does it? So we'll just type it over here. Is there that data? Is there that data? Credit card, baseball, NCI, portfolio. No, doesn't seem to be the case. So I'd imagine that when we get into the numbers, the book will take a different data set. X may represent TV advertising, Y may represent sales. Then we can regress sales onto TV by fitting this model. We haven't allowed for an error term yet. In equation 3.1, beta naught and beta 1 are two unknown constants that represent the intercept and slope terms in the linear model. Together, beta naught and beta 1 are known as the model coefficients. We will more often refer to them as the model's parameters. Once we have used our training data to produce estimates of beta naught and beta 1, so I think this is quite an important bit of info. You're kind of assuming that even if you had to play God, this is the true linear relationship. If you knew all the data, if you had all the data, if you even knew tomorrow's data, then you would know the true relationship. Instead, we can only hope to come up with an estimate of beta naught and beta 1, which doesn't give you the exact Y. Notice there isn't a hat on X. You'll always know X, and you'll use it to predict Y. You'll feed it to the model, where Y hat indicates a prediction of Y on the basis of when variable X is equal to lowercase x. Here we use a hat symbol to denote the estimated value for an unknown parameter, or to denote the predicted variable value of the response. Okay. Now, how do you actually estimate these betas? Let's see. In practice, the true beta naught and beta 1 are unknown. So before we can use 3.1 to make predictions, we must use data to estimate the coefficients. Consider the following data set representing n data subjects, where we have noted their x variable and their y variable, each of which consists of a measurement of x and a measurement of y. In the advertising example, this data set consists of the TV advertising budget and product sales in 2n equals to 100. Interesting. Different markets. So why don't we go back to 2.1? It's a pity they haven't replicated this in chapter 3, so we will have to at times go back and forth between 2 and 3. So each data point, this is really interesting. Each data point, the data subject, what does it belong to? What does it belong to? Does it belong to a person? Does it belong to a company? It belongs to a different market. So imagine maybe this observation with roughly $250,000 towards the TV budget and resulting in roughly 25,000 sales of whatever item we're offering the general public. That could be maybe in a specific country, in a specific region where they will have maybe the same programming, the same television programming. So the advert will appear, it's just in the same broadcast. So these are 200, these are 200 markets. Think of them as 200 countries, for instance, or 200 geographical regions. Our goal is to obtain coefficient estimates beta naught hat and beta 1 hat such that the linear model 3.1 fits the available data well. That is, so that yi is approximately equal to that expression for each observation I. In other words, we want to find an intercept beta naught and a slope beta 1 such that the resulting line is as close as possible to the 200 data points. Now, the word close. There are a number of ways of measuring this concept that we have a good intuitive feel for closeness. However, by far the most common approach, this is kind of just why is it so common? Maybe it was the first method, maybe computationally it's relatively easy. The most common approach, maybe just historically it tends to work, involves minimizing the least squares criterion. And we take that approach in this chapter. Alternative approaches will be considered in chapter 6. Let's have a look. So do we see this is the closeness? These vertical lines will fit a blue model to the raw red data points, and each vertical line is giving you the y difference between the actual red and the expected blue. And since we do, I think it's red minus blue, it will sometimes be positive, sometimes negative, just because the blue line isn't always below the red data. And this is why we square so that each distance is non-negative. Sometimes the distance will be 0. So for example, this is quite a good candidate. For this specific observation, the blue model, the regression, gives a very good predictor estimate. And then there are some which, it's really off the mark. For example, this distance looks quite off. Now, might be a good idea to do this in Microsoft Word to derive these formulae. Let's have a look. Let's have a look. Let y hat I is equal to beta naught plus beta 1 xi. So just assume any linear regression. Assume a model. Assume a beta naught and assume a beta 1. And could we do this in... I wonder if we could do it in Excel. I wonder if we could do it if I open... If you go into Excel, you could just imagine an x and a y variable. Let's have a look. Let's center everything. And you have your data. So for example, like this. And what I'll say over here is, I'll say 2 plus. I shouldn't be hard coding. I'm going to do it. And I'll include an error term to get something like what we have in the book. How do I include an error term? It is norm inverse of a random probability from 0 to 1. Does that not work? Do I need to specify? Hmm. Let me just try that again. 1 second. Isn't this what I need? Oh, I think it was meant to be like that. Okay. And look, we now have our chart. How do we get this? And I need, is it this one? Is it this one? Okay, so I may have taken an excessively large standard deviation. What I wanted was a line which was roughly y equals 7x. Oh, no. What on earth am I doing? I needed this and then add this. That's what I wanted. There we go. There we go. So standard deviation isn't large enough, in fact. Okay. So imagine this is your data. This is your data. And you need to, you're going to try modeling it linearly. Could we perhaps take a larger y-intercept so that, I mean, the outputs could be negative. Why not? Why not? But let's take 5. Okay. So let me fix the data. Copy Shift F10 V. So I've pasted it numerically now. And oh, something I never mentioned. You could ask Excel to do it for you. It's so simple. You could just do add a trend line, and it's telling you, do you want a linear? Do you want exponential? Do you want logarithmic? These are all different models, by the way. Polynomial, so quadratic, cubic, quartic, quintic. Actually goes all the way up to degree 6. Maybe you want a power. What's the difference between power and exponential? Not entirely sure. Moving average. And you can even include the equation, to my knowledge. Display equation. Where is it? Display equation on chart. Look, we can probably get this in R as well, if you like. We could try and see if we can get these same two numbers. I don't know if it's worth. I don't know if it's worth investing time on this. But what I would do is I'd open. I'm just gonna paste this into a new sheet and save it in my downloads. I normally just throw files that I'm only using on a temporary basis, and let's call it regression data. And I've saved it. And let's go into our studio now. Okay, so you should be able to see our studio. And we need the open XLS package. XLSX, let's load it. Okay. And what's next? I now need to say read xlsx, and we need to give them the file, which is C this, or is it this? I think it's this. In R, this is how you type it. And now just where I saved it, users, Stewart, yeah, missing T, downloads, and I saved it as regression data .xlsx. And believe it or not, that's worked. And first time round, let's save it as my data. It's in our environment. You can see it in a separate tab. Here we go. Let's go back into this. And we could see the names of the data. We just have X and Y. And we can create a linear regression model by using the function LM. LM, what is the formula? We're going to take Y and we're going to regress onto X. I think that's enough. Oh yeah, we need to give it the data. Otherwise, there isn't. How can you perform regression without data? And we'll recall my data, and this is enough. And do we get the same values as Excel? Let's have a look. 15.554 and 5.735. 15.554 and 5.735. Now, how do you calculate? What is R doing? What is Excel doing to calculate this beta naught of 15.554, the intercept coefficient, and the beta 1 with hats, right, of 5.735? Well, let's just fit. Let's take y hat. And I'm going to take beta naught hat and beta 1 hat. And for the time being, I'm just going to invent. Let's say I look at my data and I say, looks like we have a y-intercept of 20 and a gradient of 4. So I've inputted this data. Can I create a table? Well, not create a table. I just want lines. Can we choose the color white? Okay. Let's use the same font over here, like this. And these are inputs. You would normally, in any Excel file, when you're working, you use a specific color for your inputs. It is quite customary to take yellow. So I'm in the wrong. So let's take yellow. But that's not going to come up, is it? Since I'm using white text. Let's use this as my input data. Well, input parameters, right? Not data. Input parameters. So input or estimated parameters. The parameters determine the model. Well, once you've landed on a linear model, all that you need is the parameters and maybe an error term. But the chapter hasn't mentioned it yet. Okay. So I've just eyeballed these two. And in that case, what would happen? Well, y hat would be 20 plus. Shall we define the variables? You can tell Excel whatever value there is in cell C3, save it, and the shortcut is Alt M M D. And it already gives you a suggested name, B not hat. And again, Alt M M D, beta 1 hat. That's perfect. And now I can type beta naught, and it's over there immediately, and I tab plus beta 1 hat times the input variable. So in this case, 3. We're done like this. And these are my predictions now. These are my predictions. And we could probably include them in the, if I do select data, can't I add another series of data? Add X, Y, okay, okay. So the orange is the model I've used till now. It isn't what R gave us. It's not the linear trend that Excel has fitted. And do remember, R and Excel coincided in the numbers because they're using the same approach, this so-called least squares approach. Now, what is least squares? Well, let's take the difference between Y and Y hat. Okay, and that's known as a residual. It's known as a residual. We know what residual means. It's like what's left over. In fact, if I go into my browser, I'm not going to share, it will remain on the book, but I am going to look up the word residual and see what definitions come up. So residual, and I'll type definition. Residual. So remaining after the greater part or quantity has gone. That's one definition. Quantity remaining after other things have been subtracted or allowed for. Okay. And what does the book have to say about it? It is the difference. It is the difference between the actual yi and the expected. So ei for each observation, for each data subject, we're going to have an ei, and that represents the ith residual. This is the difference between the ith observed response value. So that's the actual. And the ith response value that is predicted by our linear model. Okay, so let's calculate the residuals. And this is E or EI. Of course, if I'm going to use I, then I'll have to use I. And we could do that. We could maybe say I, or just maybe bracket, or maybe this is kind of using the R syntax, isn't it? When you do a square bracket, if I go into our studio and I say my data, and I say 3, 1, that's going to give you a specific value, ij value. Let's calculate the residual. it doesn't really make a difference, but I think it's y minus y hat. It hardly makes a difference. We're going to square. And these are the residuals. The best residuals are the lowest ones for obvious reasons. So you get a very good residual over here for this data point. I can't quite, okay, I think it's working now. Yeah, it's only 6.93. There are better ones. There's negative 4.83, 5.02. You get the idea. You get the idea. Okay, so these are the residuals. Now, if you had to add, that's not really useful because you could have two very poor residuals. For example, negative 29.02 and 29.41 that practically zeroize each other. So in order to avoid that, this is where we square. This is where we're going to square each residual. So we've squared each residual. And now we're going to add everything to create a single number. And this is called the residual sum of squares. The residual sum of squares. The sum of each residual squared. Let's place it over here. This is our RSS. And it's of key importance to linear regression. So RSS. This is what we want to minimize. So R and Excel are already telling us we will minimize this with these two numbers. If I had to type over here 15.554 and 5.735, we've significantly minimized the, what does RSS stand for? The residual sum, the residual square sum, the residual sum of squares, the residual sum of squares. Whereas going back to what I took, it's approximately 8,000, whereas when we apply linear regression, we half that 8,000 to approximately 4,000. Let's leave them like that for the time being. Okay. Now, the RSS may also be expressed this way. And really, it's what we just did. This is this. And how do we calculate E1? E1 is the difference between Y1 and the predicted Y1, which, since it's a linear model, is this entire, anyway, roughly that entire thing. I mean, so speaking, this would be a plus, and then you do negative each term. Okay. Now, how are we going to minimize the residual sum of squares? The least squares approach chooses beta naught and beta 1 to minimize the RSS. Using some calculus, and who knows, maybe we could show this at some point, we can show that the minimizers are, and it's those two formulae. Now, when we say using some calculus, I do hope we haven't forgotten those optimization questions that we discussed these past few years. Only thing is, this isn't an A-level question because it's a function of two variables. Think of, for example, the volume of a cylinder. Well, that's a function of two variables, isn't it? You need your radial length, R, and you need the height of the cylinder, H. Same thing over here, same thing over here. We have beta naught and beta 1. So it would be calculus, but it would be calculus where it's multivariable calculus. It wouldn't be a derivative, it wouldn't be d by dx. It would be what we refer to as a partial derivative. Okay. I think for the time being, maybe we could take it at face value and just trust the book. So the book's telling us beta 1 is you calculate the mean of the x data. The mean of the x data. The mean of the y data. You use them so that for each observation I, you calculate the distance between xi and the mean of x times the distance between yi and the mean of y. You sum and you divide by this entire thing. This thing, and I hope I'm not saying something that's wrong, but that when we discussed variance and standard deviation these past days, that's the standard deviation to my knowledge. Well, let's have a look. Let's have a look. Let's have a look. Let's go into R. And let's see if we are able to get Excel's values using these formulae. Okay. So we need the mean of x mean. We need, or x bar, we need the mean of y. Okay. So Excel uses the command average, which is a bit confusing because averages, there are many types of averages. When we say an average, we simply mean you have data and you're summarizing an entire data set to a single value. In fact, what does Excel tell us? Returns the average, but that's very quick to elaborate the arithmetic mean. When we say arithmetic mean, we just mean the mean. There's something called the geometric mean. Used in finance, so I'm sure we will mention that at some point. So average of these x's, that's your x bar. Y bar is the average of these y's. You can give them names if you like in Excel. So Alt M M D, call it x mean. Alt M M D, call it y mean. And now we're going to calculate xi minus x mean. And then we'll do the same thing, but for y. Then we will multiply both of them. We'll multiply both of them. How should I write it? How should I write it? This times this. Okay, so let's do it. We have this minus x mean. We have over here this minus y mean. We have the product, and we go all the way down. And we want the summation of these terms. Xi minus x bar times yi minus y bar. And the summation is this over there. And now we're going to divide it. So that's our numerator. That's our numerator. We're going to divide it by this. Now, I suspect that that is the same. We've never discussed that denominator, but it's, to my knowledge, it's the standard deviation. No, not quite. Standard deviation, you have to divide by. I mean, I'm kind of speaking to myself over here because we've never defined it. Let's just do it. We need to square and add each one. So we need to take this. Let's put it. Like that. So it is this squared, like this. We take the sum, and fingers crossed, we should get this 5.735. Yep, and we do. And we do. If we round to 3 decimal places, that is 5.75. Once you have beta 1, it's quite easy to get beta 2. Because all we do is y mean minus beta 1 hat times x mean. And that is our 15.554. So these are the two formulae. Can I just double check the standard deviation thing? Because I'm curious. If I say standard deviation like this of x, and I multiply it by the number of observations, which is 18 minus 3 is 15. I need to add 1, which is 16. No, I have not. I was expecting the 340 over here. Do I need to square? Yeah. I think this gives the variance. Yes. This is the variance. Anyway, never mind. Let's continue. Although we should be concluding, aren't we? In other words, 3.4 defines the least squares coefficient estimates for simple linear regression. Now, look at this. What on earth is going on over here? Well, didn't I say that this isn't really A-level calculus? A-level calculus, you are minimizing, you're searching for turning points, minima, maxima of a curve. because the function that you are differentiating acts on a single variable. This is a harder proposition over here, although I would like us to go into the mathematics at some point, leading to this formula. Instead, it's a function of two variables. So for every beta naught and beta 1, you have a specific RSS. And for the beta naught and beta 1 that we just calculated, 5 point something and 15 point something, that's where you get the minimum of the surface. And you can even see it as a contour plot. They're the same thing. Contour and three-dimensional plots of the RSS. And in this case, our beta naught is 7.03, and our beta 1 is 0.0475. It's quite low, isn't it? As a slope, it's 0.05. Then again, you need to see in which units you're working on the scale. So look. Every dollar spent, it's a positive gradient. So every dollar spent will get you 0.0475 more dollars of sales. It's a lot easier to work in thousands, given that the gradient is less than 1. So an additional $1,000 spent on TV advertising if the model has captured enough of the relationship between it's captured the true relationship, is associated with selling approximately 47.5 additional units of the product. In figure 3.2, we have computed RSS for a number of values. Think of it as trial and error. You start plugging in beta naught and beta 1 using the advertising data with sales as the response and TV as the predictor. In each plot, the red dot represents the pair of least square estimates beta naught comma beta 1 given by 3.4. These values clearly minimize the RSS. So we have, this is 2.5 RSS, 2.3, 2.2. Minimum RSS is, less than 2.15. It doesn't really make a difference what the RSS is. You just want to minimize it. Of course, the lower it is, the better. Next session, we'll discuss assessing the accuracy of the coefficients estimates. Okay, thanks.